Let's take a look at what happens when you take a photo with a camera. First, light leaves the light bulb, hitting objects in the scene. The light reflects off of these objects and changes color, eventually landing somewhere on the camera's sensor. When light has managed to land everywhere on the camera's sensor, we have an image. One important aspect of light is that every light path is equivalent to its reverse. If a photon bounces off of a red object then a blue object, the final color will be the same as if it bounced first off the blue object, then the red. This property is called Helmholtz reciprocity. Let's apply Helmholtz reciprocity to our simple camera scene from before. What happens if we switch the direction light travels through the scene? What used to be our light bulb, emitting light in all directions, must now collect light from all directions. So we will replace it with a light sensor. Our camera measured the light coming from each direction individually, so it now must emit light in each direction. We will replace our camera with a laser pointer, which can be rotated to change the angle of emission. With just this setup, we can already take a picture from the perspective of the laser pointer by pointing it in each direction, logging the direction, and the reading from the light sensor, then plotting the readings at their corresponding directions. You might have noticed a problem by now, though. If we want to take this picture, we need to check the image sensor reading at every laser angle. This can take an extremely long time, especially when compared to the near-instant photos a camera can take. Let's think about exactly what we are doing by sweeping our laser beam across the scene. Let's call the laser dot a single pixel, and the color that pixel should be in the final image the value. In effect, by illuminating only one value, we are multiplying the scene's values by a black image with only one white pixel. When we move the laser, we're just changing the location of that pixel. Getting an image involves placing the pixel at various locations. This process of moving an image along another, multiplying them at each step, and collecting the result into another image is known as convolution. This is a modified uniformly redundant array, or mura. Muras have a special property. The output of the convolution of a mura in some image can be decoded back into the original image by yet another convolution. What does this imply? By projecting a mura onto our scene, rather than a single dot, we will be convolving our scene's values with the mura. We can later decode these to get back the original scene. As you can see, this process does actually work, and yields images from the projector's perspective. The use of muras causes much more light to hit the scene at each exposure, allowing for faster exposure times and a higher signal-to-noise ratio. In particular, if every on pixel of the mura is at the same luminosity as the single on pixel of the laser pointer, a 37 by 37 mura will be 684 times as luminous. Taking these dual photographs is useful in the real world, especially in situations where you wish to control what sort of light is hitting the scene. For example, scanning electron microscopes effectively use the laser pointer process, but with a plasma beam instead. Raman spectrometers cast one wavelength of light at a sample and determine what other wavelengths return. This is also an application of dual photography, as images are taken by either moving a laser or projecting patterns onto the sample. That's it for this tutorial. I hope you got something out of it, and thanks for watching.